Hey, welcome back to my Chemistry 12 series. Today's lecture is going to be on weak bases. Last class we introduced the concept of the strong base, the fact that it went 100% and ionized 100%, produced hydroxide, and we did the pH from that. And how do you identify those bases as well? So today's going to be about the weak bases, which mathematically speaking, they're much more complex. Although you've done weak acids with me, so back in the whole episode 6 and 7 kind of series of lectures, all the calculations that you could do with weak acids. Bases are very, very similar to what we did with the acids. It's just that a base produces hydroxide instead of hydronium. So I guess the product ion, kind of the critical ion that bases make, is slightly different. So we've got a bunch of things to get to today, so let's jump right in. I've listed the 4 things over here on the board over my shoulder, and we got to go through them sequentially, just so that we can build towards the last one, which is actually being able to do the calculations associated with it. So the first one I put up there is I guess why we're not doing something. So I'm not going over weak bases that would be considered weak Arrhenius bases. And a weak Arrhenius base would mean that it's an ionic compound that does not dissociate 100%. So a low soluble hydroxide compound. As opposed to the strong Arrhenius bases like sodium hydroxide and strontium hydroxide that we talked about last episode, where they dissociated 100%, and you could use the stoichiometric ratio easily to get the hydroxide. For the weak Arrhenius bases, you would use KSPs. So you would use a KSP to figure out what the hydroxide was in a saturated solution. Now, if it was not saturated, then the hydroxide would come out in a proportion, but the low soluble ones, they tend not to produce very much. So we would require a KSP. That was in the solubility unit. So you could go back, take a look at any calculation you did that included a hydroxide. Like let's say you did the what's the hydroxide concentration in the saturated solution of magnesium hydroxide? Well, the answer you got for the hydroxide, negative log that. That's the POH. So it's that simple. I don't need to go over that again. You've done that. So you can review that at some other point. So that's why we're not doing the weak Arrhenius one. So we're not going to look at a hydroxide compound. We're only going to look at, and you can see the title is weak Bronsted-Lowry bases. So that means you take a chemical, you dissolve it into water, and it reacts with water. Now, bases accept protons. And if you very first lecture in this entire series was what defines an acid and a base. Well, the Bronsted-Lowry base was a chemical that accepted a proton from another chemical. And when it accepts that proton, it obviously goes up in charge by 1, and whatever it took the H from is acting as the acid in that Bronsted-Lowry reaction, and its charge goes down by 1. Well, if you've got a Bronsted-Lowry base and you put it into water, the water is going to act as the acid, donating the H over to the Bronsted-Lowry base that's going to accept it. And what does it make? It makes a hydroxide, like the water. You pull an H off of a water molecule, make a hydroxide. And so hydroxide is being produced not from the dissociation of the base. It's being produced from the reaction of the base ripping an H off of water molecules. And that's where it comes from. So we need to do a calculation that involves the equilibrium constant for that type of a reaction. Okay, and it's known as a Kb. So for weak acids, it was Ka. Nice and simple. Acids, Ka. Bases, Kb. And so we're going to be using the same concepts of you need an equilibrium equation, you need an IRE table, you need to fill in the IRE table, you need to write a K expression, you need to plug in the values into the K expression that you do know, and you need to solve. So sounds exactly the same as what we did for weak acids, and it is. It's just that it's using hydroxide, and the equation's slightly different because it's producing hydroxide rather than hydronium. So let's first of all go through a couple of things. So identifying weak bases. And that's kind of one of the challenges that people have is they really kind of have beat the what's an acid, what's a base in grade. Some people even had it as early as grade 9. Certainly grade 10 and grade 11 and BC anyways. It's part of the curriculum. So it's really kind of been beat into your head that acids have the H on the left-hand side unless it's an organic acid, and then it's at the end of the Ku on the far right-hand side. And bases had a hydroxide. Well, I've been telling you that bases don't have to have a hydroxide in them. So we need to somehow reprogram your brain so that you aren't just looking for a hydroxide compound, okay, to identify what a base is. So, having said that, what types of things are we looking for when we're looking for a Bronsted-Lowry base? Well, I've listed 2 things up here. You can see them in blue under number 2 up there. So the first one is a negative charge. So if you've got anything that has a negative charge, it could be -1, it could be -2, it could be -3, it could be negative anything. If it has a negative charge, think of that as being a place to put an H+, because H+, +1, put it with a negative charge, they're attracted to each other, and it's almost like there's the negative charge is how many positions or docks or slots or whatever you want, positions for an H+ to go in. So if you had an ion that was a -3 ion, it would have 3 spots for an H+, and actually you could fit 3 H+'s into there if need be. If it's a -1, obviously it only has 1 spot for an H+. But anything with a negative charge could pick up an H. Okay, so keep that in mind. It could pick up an H. You'll notice that the second blue star over my shoulder says, why not the conjugates of strong acids? So there's a group of negative ions that don't do that. So we'll make sure we know why. We'll make sure we know which ones so that we're looking out for those ones because those will be taken out. So for example, if I gave you Cl-, you would say Cl-, oh, it's got a negative charge. It could be a weak base because it's got a negative charge. That's what he said. It's got a negative charge. It can pick up an H. Okay, so it's got a slot for an H, but because of the nature of the acid that it would have to form, it makes it a little bit more complicated. So Cl- actually isn't a base. We'll get to a little bit more detail on that in a bit. So we're looking for things with negative charges, so anions. So that's kind of the first thing. That one's fairly straightforward, and once you figure out which ones can't do it, then it's pretty easy. The second one is a little bit harder, nitrogen compounds. So a neutral nitrogen that's bound to other things has a lone pair of electrons. So I'm going to draw it, and I'm going to draw it in a 3-dimensional form. So here's a nitrogen. And I'm going to, if you think back to your Lewis dot diagrams back in Chem 11 and even in Science 10, when you were drawing a Lewis dot diagram, you kind of started with, there's varying ways of doing it, and I'll keep it fairly simple. You would figure out how many valence electrons nitrogen had, and you'd look at the periodic table and you'd try and figure out how many it has. It has 5, so you draw them going around in clockwise or counterclockwise, and then if you started going around a second time, you would pair them up. Okay, and any single electron that you had there, those had to be bonded for this to be a stable molecule. So there's a nitrogen before it's bound to anything. Then a hydrogen comes along. So here's the hydrogen. It has 1 electron, and so it comes in and it might bond right there. A second hydrogen from down here, say, here's its electron, might come in up here, and it might bond there, and then I'm not going to draw the other one. A third one could fit right there. So hydrogens with their 1 electron, easily match those single electrons for nitrogen bonds. And so N will typically make 3 bonds because it has 3 single electrons. So if they happen to be hydrogens, then you've got NH3. So NH3 is a perfect example of what we're talking about. But critical thing is that it's got that pair of electrons sitting right there. That pair of electrons acts as a dock as long as an atom comes in with no electrons. Because you can't have an atom contribute an electron to that because it's already got 2, and there's 2 that are going to be bonding electrons. So a hydrogen, like another hydrogen with an electron, can't come in because if you overlap those, there'd be 3 electrons there, and that wouldn't work. So it has to be a hydrogen without an electron. Well, the hydrogen without an electron is an H+, a proton. And that's what acids donate. So an acid can donate a hydrogen that doesn't have any electrons. And so this thing right here, because of that bonding pair of electrons, can accept an H really quite easily. And so you're going to start looking for compounds that have a nitrogen that has 3 bonds. And the 4th bond, it's not really a bond yet, but the 4th spot is a lone pair of electrons, and that acts as a perfect docking spot for a hydrogen. So it will, like if this compound, nitrogen, or NH3, ammonia, bumped into a water molecule, the water could donate an H to that lone pair of electrons and make NH4. And any other acid, any other thing that could donate an H, will easily put one on top of this nitrogen with its lone pair of electrons. Now, sometimes the nitrogen won't be bound to 3 hydrogens, but perhaps it's bound to another carbon. And then, like, you can, when you're thinking of organic chemistry, well, the possibilities are endless. I mean, you could have another carbon with hydrogens. You could have a string of carbons that was, I don't know, 10 carbons long. You could have a benzene ring, an aromatic ring there. You could have a cyclopentane. You could have a circular form of a carbon chain. You can have just about anything from the carbons coming off of there. But you'll see that that lone pair of electrons is still there. Like it's there. So you will have organic compounds that have nitrogens on them that are now, they're neutral. They've got that lone pair of electrons and they act as bases. So if you've got this situation, they act as a base. For those of you with your Biology 12, you've already gone through this. This, an H2 on an organic compound is an amino group. And that's kind of where, like, amino acid has this, and then on the other end it's got a carboxylic acid group, and so it's an amino acid. So the amino group of any organic compound actually acts as a base because the nitrogen has a lone pair of electrons that a hydrogen can dock on. So you're looking for that type of a compound. Now in Chem 12, really, we don't go into great detail. Oftentimes you're told it's going to act as a base, so you don't really have to think that one through too much, but it's a nice thing to have in the back of your head. What we will talk about, and you will be asked multiple times, is NH3. And NH3 acts as a base. If you quickly, and I'm not going to put it up to the screen. I'm not sure you're going to be able to see it, but I'll put it up there. So up here, if you look at the Ka table, NH3 is way down here. So it's like literally down here. As an acid, meaning going from here to that side, the arrow is going the wrong way. Like it doesn't go from ammonia to the other side. The arrow is coming back towards the NH3. What that indicates is that NH3 does not act as an acid. I can't tell you how many times in my own classes Students have tried to make ammonia act as an acid. It has H's, it kind of looks like it should be an acid. It's on the Ka table, but that single directional arrow going the wrong way means it's not an acid. However, the Ka table, look at this column right here. Base. You go down, go down, go down. Better stop at the right spot. There's NH3. You see that? There's NH3 going the other direction. So plus an H forms NH4. So NH3 acts as a base. And on the chart, it even acts as a base. So it picks up an H. So this is a really common one. Okay, ammonia is a really common chemical. It is quite often used in examples and in calculation questions and in labs and a whole bunch of things in Chemistry 12. So get used to it being a base. It's not an acid. Okay, don't make that mistake. It's not an acid. Okay, so on to the second blue star there. Why not the conjugates of strong acids? So, sorry, I'm going to pull up the chart again. So the chart, like I just said with the ammonia, where's the ammonia? Where was the ammonia? There's the ammonia. So the ammonia going back to ammonium, so the base is over here, plus an H, goes over there. And because there's a double arrow, that means it's possible. It can go both ways. So NH3 can act as a base to form NH4 plus 1, and NH4 can go back, lose an H, and form NH3. So both are weak, and they can kind of go back and forth, back and forth. The H goes on and off quite easily, depending on what you mix it with. And what you're starting with, I guess. Come up to the very top and take a look at all 6 of these things down here, the bases. They are the conjugate base of the 6 strong acids. There's the 6 strong acids. So when I did strong acids in, I believe it was episode 3, might have been 4, the 6 strong acids, they go 100% from the acid to the other side. So because they go 100% that away, that means this away is 0%. They go back towards the acid 0%. Now, that doesn't mean you can't synthesize these chemicals and do a reaction and form HCl. Hydrogen gas and chlorine gas will form hydrogen chloride gas really easily. It's actually explosive, big, giant, kind of cool flame. Super dangerous because chlorine, hydrogen, and then you're making hydrogen chloride gas. It's like nasty stuff. We're not doing that in the lab. Don't ask your teacher to do it. They won't do it. So you can form it synthesize-wise, but to get an H to come off of it is easy. To get the H plus to go back onto a Cl minus to form HCl ain't going to happen. And all 6 of these will not pick up an H in a Bronsted-Lowry reaction to go back to the acid. So 0%. The conjugate bases of strong acids go 0% back to the acid. Therefore, they're not bases. If it's 0%, they're not doing it. Whether you think they can or not, they don't. So you throw them into water, pretend they're going to do it all you want. They're not going to do it. Okay? And they will not take an H off of water, form hydroxide and hydrochloric acid or HBr or HClO4 or any of those strong acids. It ain't going to happen. So none of those will do it. And your Ka table kind of gives you a clue as to why that is. Okay? So the actual direction of the arrow actually matters. It's actually an important thing to grasp on that Ka table. Okay, the third thing up there. So the relationship between Ka, Kb, and Kw. So this is, you have to understand this relationship in order to be able to do the calculations associated with weak bases. So let me just kind of back up and why we need this relationship. Okay, so let's pretend I'm going to show you this generic calculation. So if we have a weak substance, if it was a weak acid, same deal as a weak base. So we have this generic substance, and we decide, okay, it's a weak substance. And you're asked, what's the pH of that solution? Well, whether it's an acid or a base, it's going to be the same steps. Step number 1, write an equilibrium that shows it acting as a weak, whatever, acid if it was an acid, base if it's a base. So write the balanced chemical equation. 2, draw an IRE table and fill in what you know. So that will always be step number 2. Whether it's an acid or a base, it's always going to be step number 2. Step number 3 is write the K expression, which is the same if it's an acid or a base. It doesn't matter. K expression. Now the K expression for an acid will be Ka equals hydronium over the conjugate base. Sorry, hydronium times the conjugate base over the acid concentration. Ka equals. If it was a base, the K expression will be Kb, not Ka, Kb equals hydroxide times the conjugate acid over the base concentration, because the reaction is slightly different. But one is the Ka equals and the base one is Kb equals. Well, thankfully for acids, we've got a table that gives us the actual numerical values of all the Kas of the weak acids we're going to be doing. We don't have a table of Kbs. So you get to that stage where you write the K expression, and then the very next step of doing any weak acid or base calculation is to plug in the values off the IRE table, plug in what you know. If you know the Ka, if you know the Kb, plug it in. If you have variables, if you have numbers, whatever you have, plug it all in and then solve for what's missing. It's always the same. Now for acids, it was the Ka, you had the number because it's on the table. So you could solve if you had a variable over in the K expression. You don't have numbers for the Kb. So if you're asked, if you've got variables in your IRE table and there are variables over on the expression side where all the concentrations are, and it's supposed to equal some number, you don't have a number. So you can't actually solve anything then. You need a number for the Kb, and you don't have it. So you need to know how to get that number. And that's why you have to understand the relationship between Kw, Ka, and Kb. So I'm not going to just give you the formula, like the little mathematical relationship. It's kind of irritating when people do this. Your teachers do it, or your dad typically does it. I'm both, so it makes it worse. My kids hate it for that reason. I can't just give an answer. I have to give the explanation. So where does this relationship come from? The relationship comes from kind of a concept where steps of a reaction, you can multiply the equilibrium constants for each step to get the overall equilibrium constant. It's kind of interesting how this works. So watch, I'm going to write the equilibrium for just the generic weak acid. Okay, so HA plus water makes hydronium and A minus, right? You take the H off of the HA. And that has an equilibrium constant of Ka, because that's just an equation for a weak acid, so therefore its equilibrium constant would be a Ka. A base, okay? If I took this thing right here and I wrote A minus, because it has a negative charge, if I wrote it in water acting as a base. Now this is all just theoretically stuff. This is not actually, I'm mixing it, and don't try and make too much out of this. If I take the A minus and I put it into water and it acts as a base, it would make hydroxide and HA. So the A minus picks up an H off of the water molecule and makes HA. The base picks up an H off of water, and the water leaves behind a hydroxide. And so there's the equation for a -1 charged ion acting as a base. That, because A minus is acting as a base, has a K expression, which is its Kb. It's acting as a base in water, so it has an equilibrium constant of Kb. So now look what happens. Kind of go way back when you're doing reaction mechanisms, way back at the beginning of the year. Anything on both sides of the equation, you can cancel. And then you can come up with a net reaction, just like step 1, step 2. And this is, again, just hypothetical. It's not like we're actually doing this. This HA cancels that HA. This A minus cancels that A minus. Anything else cancel? No. Now you add both sides, and you get 1, 2 waters in equilibrium with hydronium plus hydroxide. And everything else has canceled. Well, you've seen that before. I mean, you must have seen this. I mean, if you've been paying attention to the videos, this was episode 2, where I talked about the equilibrium of water. This is the equilibrium of water. It has an equilibrium constant. You even know what it is at 25 degrees. It's called Kw. So and you know it has a value of 1 times 10 to the negative 14 at 25 degrees. So here's kind of the critical thing. If you combine those two chemical reactions, then you cancel things and you add them all up, it comes out to water. It comes out to water's equilibrium. That means this equilibrium constant must be equal to the product of the equilibrium constants of each individual step. That's kind of a general principle that you may or may not have studied in the equilibrium unit. Depends if your teacher decided to go down that path or not. So that's the rule, which means that this equilibrium constant, Kw, equals the Ka of an acid. Okay, so I'm going to put in brackets right here, HA, times the Kb of its conjugate. Kw equals Ka times Kb of the conjugate. So as long as you know one of those two, you know the other one for its conjugate. So if you know the Ka of the base's conjugate acid, okay, listen to that wording, it's a mouthful. If you know the Ka of the base's conjugate acid, then you can solve for the Kb of the base. Okay, this is the mathematical relationship. So you know Kw at 25 degrees. You have a table of Kas. You have the numerical values down the side. Therefore, as long as you know what the base is and you can figure out what its conjugate is, you can calculate the Kb. So the Kb of any base equals Kw divided by Ka of its conjugate acid. Now it's critical that you, in your head, you say conjugate acid, not of itself, and you'll see, you might go, well, bases are bases. They're not going to have a Ka. Gets a little messier in a little bit when you've got chemicals that can be both acid or base. They're amphiprotic things. We'll get to those in a little bit. But the Kb, you're going to calculate the value of Kb by taking Kw divided by the Ka of its conjugate. And so on here, if you go down the right-hand side, if I give you, I don't know, Cn minus is the base, so cyanide. So you go down and you find Cn minus, Cn minus, Cn minus, Cn. Oh, here it is, right here. It's over here on the right-hand side. It's acting as a base as it goes from the right to the left over to HCN. The Kb of Cn minus, okay, which is right here, would be equal to Kw, 1 times 10 to the negative 14, divided by the Ka of HCN, which is right there on the table. Like if you can find the line where Cn minus is on the right-hand side, or whatever base you're talking about is on the right-hand side, it's conjugates over on the other side. You're on the line that has the conjugate acids Ka. And that's what you're going to plug in to solve for the Kb of that chemical. Now, think about this one. Here's a little mathematical logic. That as you go down, the Kas get smaller and smaller and smaller and smaller. So you're going to be dividing by a smaller and smaller and smaller number. That means the Kb going back the other way is going to get bigger and bigger and bigger and bigger and bigger. So up here we've got reasonably high Kas. Therefore, the Kb's of the bases on this side are not going to be very high. They're probably going to be pretty small. Down here, the Kas are getting really, really, really small. And because they're getting really, really small, the Kb's of the bases going back the other way are going to get bigger and bigger and bigger and bigger and bigger. That's why this arrow says increasing strength of acid. This arrow over here, increasing strength of base, and they're opposite to each other. And so that's kind of an interesting little relationship between the Kb of a base and its conjugate acids Ka. As one gets bigger, the other's got to get smaller, so they still multiply to Kw. Now let's actually use that Kb principle to go on to the fourth step here, and let's calculate the pH of a weak acid solution. So let's do one fairly straightforward. And again, you'll see kind of where all this stuff fits in, how the Kb fits in, and what the equation looks like. It's slightly different, but same general concept as the acids. Again, the K expression slightly different, but same general concept as the acids. And I'm not even going to do all the different intricate little changes that we can do to the calculations, because they're really the same thing. It'd be redundant. It'd be a waste of your time. So you can go through and say, oh, okay, so before we did Kas, and this is the technique that he used to get the Ka of a weak acid, let's use the same technique for getting the Kb of the base. And so you'll be able to transfer back and forth. Okay, so let's put a question up here. Okay, so what is the pH of let's go with a 2.2 molar solution of F minus fluoride at 25 degrees Celsius. Of course, I have to say 25 degrees Celsius because the table uses that 25. So if I didn't say that, then the whole thing gets thrown for a loop because your Kb can't be calculated. Okay, so let's go through the steps again. They're the same for acids or bases. Write in an equation, a balanced equilibrium equation. IRE table, fill it in with what you know. K expression, plug in the values that you need, solve, and then see what you have to do to actually get your answer. So I asked you pH. Okay, so first things first, it's not challenging to figure out what this thing is. So it's F minus, has no H's, so whether it's an acid, that's out of the question. Like, that should leave your head. Can't be an acid, hasn't got an H. F minus, so it's got a negative charge. It fits kind of into that category of could be a possible base. But is it one of those conjugates of a strong acid? No, obviously I wouldn't be asking the question if it was. But you should know off the top of your head what those 6 are so that you don't kind of sit there and go, well, F minus, I don't know about that. You should know them right off the bat. So F minus is not one of those 6. HF is not a strong acid. So F minus, in fact, will act as a weak base. So I write in an equation having F minus acting as a base with water. So here's what it looks like. F minus, it's aqueous because it's an ion, so it would have to be aqueous, plus H2O. It's a weak substance, so you're using an equilibrium arrow. Forms. Now, I typically write it, like I write hydronium, then the conjugate base. So in this case, I'm going to write whatever the H goes on to, I tend to write it first. There is no rhyme or reason to it, it's just my weird brain. So I take an H, take it off the water, put it on the F minus, it goes to HF. It's now neutral because it was -1. I put a +1 on it. Plus hydroxide. So the water has an H ripped off of it. There's the hydroxide. So there's my balanced chemical equation, all the phases, all the charges. Cool. IRE table, or ICE table, as it were. IRE. Cross out the water. Because water is liquid, doesn't change concentration, not put into any K expressions, not part of any KQ. I know the initial concentrations, so I know the initial F minus is 2.2. I know this is 0 and that is 0, or for all intents and purposes, there's 0. I don't know anything on the equilibrium line, but I do know it's going to go towards 0 as it gets to equilibrium, which means these are going to go up. This is going to go down. They're all in a 1-to-1-to-1 ratio. I don't know how much, so they're all going to change the same amount. So they will be X. 2.2 minus X. 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 Okay, so there's my IRE table filled in. K expression. KB equals HF times hydroxide over F minus. Right? So now I'm going to plug everything in. So I can plug in stuff over here, no problem. KB is a bit of an issue though. So the way that I like to do it is you don't need to show it over on the side or anything like that. You can just write KB in a different form. KB equals KW divided by KA of its conjugate. So I would almost write, not almost write, I would write KW, whoops, no, well, that's fine, KA of HF, right? It's not just generic conjugate acid because the conjugate acid is HF. If you're uncertain what the conjugate acid is, it's the one that gets formed. So if F minus is the base, its conjugate is what it makes. So HF is the conjugate acid. So I would do that. Now, to kind of cut to the chase, I would now write down those numbers. So 1.0 times 10 to the negative 14 over, okay, so now I got to be careful. So I'm looking for HF on the periodic, or on the Ka table. So I'm looking for HF, and it's right here. Okay, so it's right there. HF, and its Ka is 3.5 times 10 to the negative 4. 3.5 times 10 to the negative 4 equals. And now I would kind of carry on here, and I would just plug in my equilibrium values. So x squared, that's x, I'm cutting to the chase, x squared over 2.2 minus x. I make the assumption. It's, like I said, it's literally exactly the same thing that you did with weak acids. So same technique. Just when you get x, it's going to be hydroxide instead of hydronium. So assume. So I'm going to assume x is significantly less than 2.2, and if my assumption doesn't work, then I know how to deal with that because I learned how to do that in episode, I think it's 7E. So now I pull out the calculator and I'm doing this. I mean, I like to do this. I'll do it, so I'll write it down. So I'm going to do 1 exponent negative 14. Hang on, I need my glasses. I'm trying to do it without glasses. I can't see it. Divided by 3.5 exponent negative 4 equals. And so I'm going to write that down. Now I'm going to write down the rounded version, but I'm going to keep the unrounded version on my calculator for the next step. Okay, so it's just going to hold still there. So this comes out to 2.9 times 10 to the negative 11 equals x squared over 2.2. Okay, still on my calculator. I'm just going to give myself a little bit of room here. Okay, and like I said, I mean, really, you don't have to show it at this. Once you write this down, you can just say x equals on the next line. You don't have to show that you're multiplying by 2.2 and then you're taking the square root. Everybody knows that that's what you're doing. So x is going to equal, I'm going to multiply by 2.2, then I'm going to square root that. So times 2.2, and then I'm going to square root the answer, and I get 7.9 times 10 to the negative 6. Okay, now that's the hydroxide concentration. So you can actually write that down. So X equals the hydroxide concentration, which is that. So it's not very high because it starts in distilled water at 1 times 10 to the negative 7. And this is kind of a crappy base. I mean, it's 2.2 molar. It actually starts out pretty concentrated. But it's not very good, low Kb. And so it doesn't produce very much. Now, technically, we should be taking this value and adding 1 times 10 to the negative 7 to it, because we're supposed to be taking the total amount. So actually, this should be plus 1.0 times 10 to the negative 7. And one of the critical things you should be looking at is maybe that exponent. So if you get something like 10 to the negative 6 on your molarity, then you should be considering, just try it, add 1 times 10 to the negative 7, and see if it actually changes it to something that's, right, if that goes from 7.9 times 10 to the negative 6 up to 8.0, which is going to, 8.0 times 10 to the negative 6, then you're supposed to be including it. So I do that math, and sure enough, it equals 8.0 times 10 to the negative 6 molar. So that should be the number that I'm using. So I'm just going to add that in just so I've got it on my calculator. Okay, so that's my hydroxide. I negative log that, and do I get the pOH or pH? I get the pOH because it's hydroxide concentration. So pOH is typically, if you negative log the answer that you get for a weak base, you're going to get a pOH. So you always got to remember that. So the pOH equals negative log of the hydroxide, which equals 8.0 times 10 to the negative 6, which, let's take the log of our answer, and I get 5 point, and there's 2 sig figs, so it comes out to 5.10. Now, don't let your brain freak out. 5, oh my goodness, it's less than 7. This is a POH. So don't freak out. Concentrate, focus. pH plus POH equals 14, right? So pH plus 5.10 equals 14. pH equals, and you subtract 5.1 from 14, and you get 8.90. And that's your answer. And that's a base solution at 25 degrees. So we're good to go, right? We're happy about that number. It comes out to what it's supposed to be, the 2 sig figs. So weak base calculations, they look really similar. Like if you just kind of took a picture of this and didn't really pay attention to what the equation was saying and the fact that it said hydroxide, it looks like the weak acid problem that we did way back when, with some minor differences. The equation's different and it produces hydroxide. It's a Kb instead of a Ka, and the Kb takes a little bit of manipulation of how do you figure that value out, Kw divided by Ka of the conjugate acid, and then your answer is going to be a hydroxide concentration. So you can't just get a pH from that. You have to negative log it, get a POH, subtract from 14, and you're good to go. So that's the weak base concept. Okay, and again, any of those kind of weird, tricky little types of questions where I could ask you, here's some information, what's the Kb of the base? Well, maybe the IRE table is filled in with nothing but numbers, and so you can get the Kb. Because you know the relationship between Kb and the Ka of its conjugate, maybe I ask you to solve the Kb and then ask for the conjugate acid, Ka. I might ask you, what's the initial concentration of the base? There's a whole bunch of different things that you could do that look very similar to the weak acid stuff. So the techniques are all the same. So that's it for weak bases. You can apply those skills you learned earlier to bases, given the opportunity. So next class, I'm gonna introduce the concept of a polyprotic species. So an acid that has more than one H to give up, and bases that have room for more than one H to join. And you'll see actually that once you get the concept of it, mathematically it's not that challenging. It's quite simple actually. You'll see that the second spot doesn't usually mean anything. So you just have to understand that concept. Okay, so we'll see you next time. We'll be talking about polyprotic acids and bases.